All right, so today is our last lecture of the complex analysis seminar. For now, I might pick it up in the future, but it's going to be probably months down the line. But I wanted to talk about one of my favorite theorems in complex analysis, which is the residue theorem, which is a generalization of Cauchy's theorem, which we already talked about. So in order to talk about that, I need to tell you what residues are. Um, and they're pretty simple to state. So suppose you have Z0 and it's an isolated, come on, pen, isolated singularity of F. So what does that mean? That means F does something funky at Z0. It might diverge, or maybe the function's not defined there, in which case you have a removable singularity, or whatever. Something you don't like happens there. Um, and and the isolated part just means that we don't have like a continuum of singularities. We can separate them by some open set. And f of z has the Laurent series again, and some of these negative coefficients or negative index coefficients might be zero. Maybe only finitely many of them are um, non-zero, in which case you have a pole. Maybe infinitely many of them are non-zero, in which case you have an essential singularity. Uh, Maybe they're all zero, in which case you have removable singularity. And we're going to assume that this holds in the punctured disk of radius rho for some rho. Okay. Why the punctured disk? Because we have a singularity there, and we assume it's isolated, right? So there's not another one nearby, and so there's no reason to think about an annulus because we're analytic, uh, within a neighborhood of z0. Okay, so the residue of f at z0 is the coefficient a minus 1. That is it. That is a residue. And now I will tell you a little more detail. um, so first of all, the notation we write for residues is the residue of f at the singularity z0 is a minus 1, which we remember from Cauchy's integral formula, or sorry, not this would not be Cauchy's integral formula. This would be Cauchy's integral formula. In any case, we've proved this identity for the coefficient a minus 1, where here r is any fixed radius satisfying 0 less than r less than rho. Okay, yes, that is Cauchy's integral formula. I remember the exponent had a uh, uh, power plus 1, right? And so the minus 1 cancels it, we get 0. Okay, so as an example, the residue of 1 over z at 0, right? 0 is indeed a singularity, and the residue is, well, what's the coefficient of the z to the minus 1 term? Well, it's just 1. The entire power series is 1 over, or the entire Laurent series is just 1 over z. And the coefficient a minus 1 is 1. The residue of 1 over z minus z naught squared at z naught will be 0 because there is no a minus 1 term here, right? So a minus 1 must vanish. Another example would be 1 over z squared plus 1, but it's not in the correct form yet, right? This is not in our power series form, but we can write it using a partial fraction decomposition as 1 over 2i, 1 over z minus I, minus 1 over z plus I. And then this is equal to 1 over 2i, 1 over z minus I. And this guy we can write as, well, we can expand it as an analytic function in z minus I, right? Certainly that's not a problem here because we don't have any problems with z being equal to I. So I'm just going to write plus something analytic. What does that mean? So there's no minus 1 term here. So that tells me that the residue of 1 over z squared plus 1 at I, right, that's where my singularity is 1 over 2i. Okay, so there is also a singularity at minus I here, right? But I could do basically the same thing, but I could expand this guy instead as an analytic function in z plus I. Okay. All right. So now I can finally tell you the residue theorem. Now that we know what residues are. So this is the residue theorem. It says if D, so let D be a bounded domain and C with, this is important, with piecewise smooth boundary. This is going to tell us what kind of contours we're allowed to use. Suppose F is analytic on D union its boundary, except for a finite number of isolated singularities. Let's call them Z1 through Zm, and they should be in that domain D. Then what we have is that the integral along the boundary of D of our function is in fact equal to 2 pi I times the sum of the residues. And the proof is not hard at all. So what you do is, well, first let me draw a picture. We have some domain, maybe it looks something like this, where this is D, and it has some singularities. You know, here's Z1, maybe we've got another one here. Let's say we've got 3, so we've got one here as well. What I'm going to do is I'm going to puncture the domain to remove these singularities. And instead of considering d, I'll consider d epsilon. So I'm assuming all of these are radius epsilon here. So I'll consider instead the domain d epsilon, which is given by, well, we have the boundary of d, and then we've also got this boundary along each of the punctured disks. Okay, so the domain I'm considering is, all of this stuff, nothing inside the disks. Okay, so let's write that down. Let d epsilon be the domain obtained by punching out small disks. We'll call them uj, centered at zj. So zj being each singularity. And we'll assume it's of radius epsilon. Okay. So remember the formula for the residue at zj, we have the residue of f at zj. This is the a minus 1 coefficient. And by the Cauchy integral formula, we can write that as 1 over 2 pi I, the integral over the boundary of uj, right? That's this little circle here, and here, and here, of f. Okay, so we'll keep this fact in mind. And then what we do is we just apply Cauchy's theorem with the domain d epsilon instead of d, right? Because the function f is analytic on d epsilon, because we've removed all the singularities. So Cauchy's theorem tells us that the integral along the boundary of d epsilon, which is the boundary of d, union the boundary of u1, union the boundary of u2, union the boundary of u3, and so on. Right? So what does that look like? That means by Cauchy's theorem, I've invented a new letter, the hy. By Cauchy's theorem, we have that the integral along uh, d epsilon is equal to 0. And what is this? Well, this is the integral along the boundary of d minus the integral along the boundary of uj, and we're going to sum over these. So y minus, because the arrow here goes in the opposite direction. So, okay. So whenever we describe a domain like this, we had the convention that the arrow points in such a direction that the domain lies to the left. So if I'm traveling along the boundary like this, to my left, the domain is here, and so that's why I put the arrow here. Right? Now, the domain here, so if I'm traveling along the edge of this disk, the domain is to the left if I travel in this direction, which explains the arrow for each of these. But when I consider the integral along the boundary of uj being each of the disks, now suddenly, the proper thing to do, well, the domain I'm considering is the inside now, right? And so now the arrow is pointing in the opposite direction. And so that's why I need this minus sign. Okay. So this tells me that the integral along the boundary of d is equal to, well, it's the sum of each of these integrals here, but each of these integrals is in fact 2 pi I times the residue. And so this tells me that the integral along the boundary of D is in fact 2 pi I, the sum of the residues. All right. So hopefully that was understandable. It's just a simple consequence of Cauchy's theorem, but doing a clever trick where we remove the singularities. All right. So before I get into the examples, let me give you a few useful rules for calculating residues. The first is that if F has a simple pole at Z0, then the residue of F at Z0 is just the limit as Z goes to Z0 of Z minus Z0 F of Z. So remember, a simple pole is one which has order 1. So only the A minus 1 term is non-zero in the Laurent series expansion. So that means that F can be written as A minus 1 over Z minus Z naught plus the analytic part. So this is, the terms with A0 through, A infinity, right? The point is that there are no further negative terms. So in order to recover the residue, we need to recover this coefficient A minus 1. So how do we do that? Well, we multiply by Z minus Z0, then we take the limit, and we find that well, this is equal to the limit of A minus 1 plus Z minus Z0 times this analytic part. And what's that limit going to be? Well, it's just going to be A minus 1. And that's the residue. Okay, so if you know you have a simple pole, multiply by this Z minus Z naught, and then take the limit. This extends to double poles with the introduction of a derivative. Then the residue is the limit as Z approaches Z naught of the derivative of Z minus Z naught squared times F. Okay. And so the proof is more or less the same. Now you can write F as, since it's a double pole, that means as order 2, it's A minus 2 over Z minus Z naught squared plus A minus 1 over Z minus Z naught plus the analytic part. So you multiply by the Z minus Z naught squared, that gives you an A minus 2, and then an A minus 1 times Z minus Z naught plus, Z minus Z naught squared times something analytic. So when you take the limit, if you took the limit there, what you would get is the A minus 2 term. That's not what we want. We want the A minus 1 term. So now we take the derivative. That gets rid of this guy, and we're left with A minus 1 plus something analytic that goes to 0 in the limit. So more or less the same proof. Okay. And that those rules do extend further to arbitrary n, and you can look up the formula if you wanted, probably on Wikipedia, but I didn't write it down, so I think it's something like if you have a pole of order n, then your residue will be limit as z goes to z naught of d n minus 1 by dz n minus 1 z minus z naught to the n f of z. Yeah, that makes sense. Okay, so there's your general rule for poles of order n. Okay, but rule 3, if f and g are analytic at z0, and if g has a simple pole, a simple zero, so that the quotient has a simple pole at z0, then the residue of the quotient f over g at z0 is given very nicely by evaluating the function f at z0 and then evaluating the derivative of g at z0. Okay, so the proof of this is just an application of rule 1. Well, maybe it's worth looking at. So you have the limit as z goes to z0. So this, what we're computing right now is the residue of this quotient, right? The fact that g has a simple 0 at z0 means the quotient has a simple pole, which means we can apply rule 1. So the residue is z minus z naught times the quotient in the limit. But this is equal to the limit as z goes to z0 of f of z over g of z minus g of z0 over z minus z0. I just realized I don't know where this term comes from.
I mean, it's 0 by assumption.
Yes, thank you. Okay, so we take the limit and we get f of z0 over g prime of z0, right? Because this is our difference quotient. We take the limit, it becomes the derivative. Thank you, Logan. Okay, and then rule 4 is just a corollary of rule 3, but it happens frequently enough that we mention it. So if f equals 1 and g has a simple 0, then we have the nice formula residue of 1 over g at z0 is equal to 1 over g prime z0. Okay, so just apply rule 3, set f equal to 1. All right, so these are the nice rules that usually get used when computing residues. They're the only ones that Gamblin mentions, and so they're probably sufficient for any exercises in his text if anybody wants to do them. But without further ado, let's do some examples. So here's an integral that you probably know how to compute. And I'm going to give you a much longer, more convoluted way of computing it just to show you how the residue theorem works in practice. Okay. So, antiderivative of this guy is just going to be arctangent, right? And so you could compute this very easily if you wanted to. Okay, so the way this usually goes is we first draw a contour. What contour you draw, you kind of learn from experience. Let me draw one for you for this problem. One of the things that you consider when drawing a contour is where the poles are going to be for your integrand. And here we have poles of this polynomial or this rational function at, I don't want to, I don't, maybe step 0.5 or step 0 is replace the x's with a z so that you're integrating in the complex plane. And the poles are going to be at plus or minus I here. So we'll have a pole here, and we'll have a pole here. And now I'm going to draw a contour without much justification, just because I know it's going to work. But if you do enough of these, you will realize where they should go. So we're going to draw a contour from minus r to r for some parameter r that we're going to let go to infinity at some point. And here are our arrows indicating the path. And we'll call this arc here, we'll call this gamma r. And the entire contour here, we're going to call, what do I call it in my notes? dr. Well, actually, the region on the inside is dr. And so minus r to r union with gamma r is the boundary of dr. Okay, so I have one of my singularities inside of my contour. So I wrote step 2, but maybe this should go before step 1. Identify the poles. Inside dr. So in our case, poles are plus or minus I, and only the plus I pole is inside of the contour. Step 3, compute the residues. And we only need to compute the residues of the poles inside of the contour. So in our case, we have the residue of 1 over z squared plus 1 at I is, well, we actually already computed this one earlier. This is, well, let's go ahead and use that last rule. Let's use rule 4 here. This will be 1 over the derivative of z squared plus 1. That's 2z, evaluated at z equals I. That's 1 over 2i. Step 4, we need to compute the value of the integral over the boundary of dr. And this is where the residue theorem comes in. Okay. So the residue theorem tells us that this integral is equal to 2 pi I times the sum of the residues. There's only one residue here, right? It's 1 over 2i. So what we get is pi. And yes, this pi matches that pi, but the integrals are different. So now what we want to do to finish this off is show that this integral is in fact equal to this integral up here as r goes to infinity. So how do we do that? Well, step 5, we basically write the integral along the boundary of dr. We split it up into the integral from minus r to r plus the integral along gamma r, right? So the integral along here plus the integral along here. And this will be the integral you want plus the other junk. Other junk you hope is 0. And now what we want to do is show that the other junk does in fact go to 0 as r goes to infinity. Okay, so how do we do that? Well, the other junk in this case is the integral along gamma r of dz over z squared plus 1. And we can bound this by integral over gamma r modulus of dz over modulus of z squared plus 1, which is less than or equal to the integral along gamma r of the modulus of dz times 1 over r squared minus 1. So this comes from, it looks like reverse triangle inequality. Yes, okay. Yeah. So we have z squared plus 1 greater than or equal to absolute value of modulus of z squared minus 1. And along this contour, this will be an r. Okay, and then this is now, so the r is independent of the integration variable. And so all we're getting here with this integral is the arc length, right? And the arc length of that semicircle is just going to be pi. Pi.
You'll eventually take a limit and it works out still. It's pi r, but yeah.
Yeah, pi r, right? Yes, pi r. Yeah. Sorry, for some reason my mind blanked on why the r was there, but no, it absolutely should be there. Circumference of a circle is 2 pi r. Okay. All right. Anyway, so this goes to 0 as r goes to infinity, right? And so, in fact, as r goes to infinity, this integral does indeed go to 0, and so the integral along this arc term doesn't matter at all. And so, step 6. Profit. So the integral from minus r to r as r goes to infinity becomes the integral from minus infinity to infinity of our function. In this case, it's dx over x squared plus 1. I replace the z with an x because we're along the real axis now. And then this term goes to 0, so we just showed. And so this is equal to the integral along the boundary of dr of dz over z squared plus 1. Right? But this, we already showed by the residue theorem, was equal to pi. Okay, so that's all there is to it. You construct a contour that contains some poles, and the way you construct it is so that the pieces that aren't going to give you the integral you want, those terms go to 0. Right? Or, I mean, they don't have to go to 0. They could be something that's easily computable if you wanted. And then you would just have to, subtract some things instead of something vanishing. Okay? So that's a perfectly reasonable thing that can happen. But usually what we'll find is that this extra term just goes to 0. In fact, when people use this technique, oftentimes they just assume it does. People don't like to be bothered with showing that it does in fact go to 0. But that can lead to problems if it doesn't in fact go to 0. Okay, here's another example. Zeros on the real axis. Okay, so if you want to take the integral from minus infinity to infinity of a rational function like this, you can do it using the same exact contour as long as there are no zeros on the real axis. Okay? If there are zeros on the real axis, well, then you have to kind of play with it a little bit. And I don't know if it works out, but I could see it maybe working. We'd have to work out the details. But anyway, so you just follow the same exact procedure with this guy. Some things that you will need are for convergence of the integral, you need the degree of q to be greater than or equal to the degree of p plus 2. So we use the same contour as before, and what we find is that the integral from minus infinity to infinity of p of x over q of x dx. So using this assumption, I think we can show that that arc term goes to 0. But what we'll find at the end of the day is that this is the sum, 2 pi I times the sum of the residues of this rational function, where the sum is over all residues. Residues in, what did I call it, DJ? Well, we're letting R go to infinity. All residues in the upper half plane. So remember, with that contour, we have that semicircle on the top. As R goes to infinity, it covers the entire upper half plane, right? Okay, so yeah, I mean, it's this almost the same problem for any other rational function. So as long as you have convergence, you can compute the integral of the rational function in exactly the same way. Okay. The only thing we didn't do here was argue for the arc term going to 0. Okay, so we do another example. So this example is of a different flavor. We're not going to write this as a contour containing the integral we want plus other junk. Instead, we're going to transform this integral into an integral in the complex plane. Okay, so we're going to do that by writing z equals e to the I theta, so that dz is I e to the I theta d theta, which is I times z d theta, which tells us that d theta is dz over iz. Okay, so we can write cosine of theta as e to the I theta plus e to the minus I theta over 2, which we know is z plus 1 over z over 2. So with this substitution, what our integral becomes is, let's call it I so I don't have to rewrite it. Our integral becomes the integral from along the circle of radius 1, right? As theta goes from 0 to 2 pi, we're tracing out the circle of radius 1 in the complex plane of 1 over a plus 1/2 z plus 1 over z. And then d theta is dz over iz. And this is 2 over I, the integral along the circle, radius 1, of dz over z squared plus 2az plus 1. Now, we know where the poles of this guy are by the quadratic formula, right? So the roots of this polynomial here are given by the quadratic formula. They're at minus a plus or minus the square root of a squared minus 1. Okay. Now, if you plotted this guy and recalled the assumption that a is greater than 1, what you'll find is that only minus a plus the square root of a squared minus 1 is inside the unit circle. Okay. So that's the only pole we're concerned with. The other one, we can throw it away. Okay, so now we compute the residue. There's no arc term that we have to argue goes to 0 or anything like that. All we've done here is transformed the original integral into an integral in the complex plane. And now we're going to use the residue theorem to compute it. Okay. So all we need to do is compute our residues. So the residue of the function 1 over z squared plus 2az plus 1 at z0 is equal to z0 being this guy here. I'll write that. Is equal to 1 over 2z plus 2a. So I'm using rule 3 here. Well, actually, I guess it's rule 4. Special case. So it's this guy evaluated at z equals z0, which is this quantity. And we plug that in, and what we get is 1 over 2 square root of a squared minus 1. So what does that tell us? Well, that tells us that the integral, the original integral from 0 to 2 pi of d theta over a plus cosine theta, what we did was we transformed it into an integral in the complex plane. And the residue theorem tells us that that integral in the complex plane is equal to 2 pi I times the sum of the residues. There's only one residue here. And I'm missing a factor of 2 over I that's hanging out over here. And this is 2 pi over square root of a squared minus 1. Okay, so I do not know how I would have computed this without complex analysis, actually. I don't know, maybe one of you can figure out a clever way to do it, but I don't know myself. Okay, so, let me point out something. I wanted to point out that the result of this integral hinged on the fact that we could figure out where the roots of this this polynomial here are. Right? And one of the oldest problems in algebra is figuring out where the roots are for an arbitrary polynomial. And it was shown using group theory that there's no formula for the roots of the polynomial here for any polynomial with degree greater than 4. So there's a formula for degree 1, 2, 3, and 4 for the roots of the polynomials in terms of radicals and other simple functions. But as soon as you get to degree 5 and up, such a formula does not exist. And apparently, recently it was shown by N.J. It's Wildberger that for the polynomials of higher degree, you actually can come up with a formula, just not in terms of radicals. Instead, the formula is related to these extensions of the Catalan numbers. Okay. All right. So the last thing I want to do is talk about Ramanujan's master theorem. And I'll only give you like a sketch of a proof. The nitty-gritty details are not worth going through. I just want to show you how the residue theorem is used to prove this result. And disregard all the other issues like convergence and so on. So let G be an analytic function on the half plane H of delta Z and C, real part of Z greater than or equal to minus delta. I will state the nitty-gritty details just so you know. For some delta between 0 and 1. We have to assume that A is less than pi and G satisfies a growth condition, which looks like G of V plus IW is less than or equal to a constant C times E to the PV plus AW, where this A again is less than pi. You can show that this bound here is sharp. There's an example where if A equals pi, then this fails. For all Z equals V plus IW in the half plane. Then the integral from 0 to infinity of x to the s minus 1, sum from k equals 0 to infinity, minus 1 to the k, g of k, x to the k, dx, has this nice formula. It's just pi over the sine of pi s times g of minus s. And this holds for all s with real part of s between 0 and delta. Okay. So this quantity here, so let's call this guy f for a second. This quantity is called the Mellin transform. The Mellin transform of f. And there's an inversion formula for the Mellin transform, which tells us, grab that really quick, make sure I get that right. Which tells us that the inverse Mellin transform of a function phi evaluated at x is 1 over 2 pi I, the integral c minus I infinity to c plus I infinity. So this is an integral along a vertical line in the complex plane. That's what this notation means. X to the minus s, phi of s, ts. So this guy is the Mellin transform. This guy is the inverse Mellin transform. So if I take the inverse Mellin transform of the Mellin transform, I should get back f. And there is a theorem that tells us that that does indeed happen under some conditions. Okay. So how do we prove Ramanujan's master theorem? Well, we instead of looking at this integral, what we can do is look at this integral and prove some result about this integral in the complex plane using the residue theorem, and then apply the Mellin inversion theorem to get back to the original function here. So let's go ahead and do that. All right, so here's a sketch of a proof. All right, so we're going to consider the integral 1 over 2 pi I, the integral along c of pi over sine of pi z, g of minus z, x to the minus z, dz. Let me pull up the inverse Mellin transform again so you can see what I'm doing. Okay, got my 1/2 pi i's. Now, I haven't told you what C is yet. It's not going to be this vertical line. It's going to be the vertical line plus a completion of the contour. So I'll draw it in a second. And then we have our x to the minus s. I use z here. It doesn't really matter. It's a dummy variable. And then our phi, this guy, is the rest of this. So it's this part here. This is our phi of z. Okay, so C here is going to be the left semicircle contour. So little c, let's say it's this guy here. So little c is the little c that appears in the melon, the inverse melon transform. So remember the contour for the inverse melon transform is this vertical line here, like this. And now what we're going to do is complete the contour by a semicircle that goes into the left half plane. Okay. So what do I call this? I call this gamma. The semicircle arc part, I'm going to call it gamma. And this is my part from C minus I infinity to C plus I infinity is the usual notation. Okay. Now we can show, I'm not going to do it because I don't want to, that the integral along this arc term goes to 0. So I've selected some r here. Times I, as r goes to infinity. And how do you do this? Well, you use the growth condition in Ramanujan's master theorem. Okay, so that tells us that this guy, the integral along here, doesn't matter. Okay. Now, if we apply the residue theorem, well, where are the poles? Right. Look at our integrand here. This guy's analytic. That guy's assumed to be analytic. And then this guy has poles at minus n for all integers n. Well, plus or minus n actually, but the only ones we're concerned with here are the ones that are inside the contour. And those are the ones at minus n. We can compute the residues of those. They're all simple poles. We can compute the residues. And this comes out to pi times, there's going to be a limit. I'm going to use another trick here for computing residues that I didn't mention earlier. C plus n over x to the z sine of z. So whenever you have an analytic function, and you want to compute the residue. So if you have a product of two functions, one of which is analytic, the other one is the problematic one, which is not. When you if the poles are simple, then when you take the residue and you take this limit, you can just pull the analytic function outside. So that's what I did here. And this is equal to pi g of n, the limit as z goes to minus n. So what I'm doing here is a L'Hopital rule. I ran out of space, but we have a plus pi x to the z cosine of pi z. So again, that was L'Hopital's rule. I have an indeterminate form here of 0 over 0. Okay, and then now I take the limit, and this gives me pi g of n over pi minus 1 to the n, x to the minus n, which rearranging things is minus 1 to the n, g of n, x to the n. And this should look familiar. These are the terms of the function f and its power series representation. Okay, so what does this tell us? This tells us that by the residue theorem, this integral 1 over 2 pi I, integral from c minus I infinity to c plus I infinity of pi over sine pi s g minus s x to the minus s ds is equal to the sum of the residues, but the residues are these guys. This guy is just f. And this is the thing we called phi, right, in the inverse Mellin transform. So now if I take the Mellin transform of both sides, what I find is that, well, I have an inverse Mellin transform of phi here, right? So that just becomes phi itself. And then over here, I take the Mellin transform, and that's the integral from 0 to infinity, x to the s minus 1, sum from n equals 0 to infinity, minus 1 to the n, g of n, x to the n. And then I'm done. Got my dx. Now I'm done. So that's the basic idea behind Hardy's proof of Ramanujan's master theorem. I mean, it's really just the residue theorem done cleverly with a little machinery behind the scenes using the maybe not behind the scenes, but a little extra machinery in terms of the Mellin inversion theorem. So we need to know the Mellin transform and its inverse exist, and then they do indeed cancel each other in order for all this to work. Any questions? I think I will conclude with maybe I'll conclude with my favorite proof of the Gaussian integral. This guy. So this is equal to the integral from 0 to infinity of the sum from n equals 0 to infinity of minus 1 to the n, 1 over n factorial. Another way to write that is 1 over gamma of n plus 1, x to the 2n dx. So I've got a problem here. So I want to use Ramanujan's master theorem, which I wrote down right here. But notice I have a k here. In my case, it should be an n, but I have a 2n. What do I do? Oh, well, it's just a substitution. So set u equal to x squared. Du equals 2x dx. And so let's see. X dx is 1/2 du. And as x goes from 0 to infinity, u also goes from 0 to infinity. So this is an integral from 0 to infinity, sum from n equals 0 to infinity, minus 1 to the n, 1 over gamma of n plus 1. And now I have u to the n, and then I have this dx is, I'll write it as 1 over 2x du, but what is x? It's just the square root of u. Okay, so that's the same as integral from 0 to infinity of u to the minus 1/2 I'll pull the 1/2 out front. Sum from n equals 0 to infinity minus 1 to the n, 1 over gamma of n plus 1, u to the n du. Now I can apply Ramanujan's master theorem. This is my g. Right? And then what is my s? So remember this is supposed to be s minus 1. And so s must be equal to 1/2. Hopefully I haven't screwed up here. That looks right. Okay, and so this should be equal to 1/2 pi over the sine of pi times s. We said s should be 1/2. So pi times s is pi over 2 times g of minus s. So that's 1 over gamma of 1 minus 1/2. That's 1/2. And this is pi over 2. Sine of pi over 2 is 1. And gamma of 1/2 is well known. This is the square root of pi. Don't ask me to derive it. So this is the square root of pi over 2. So that's how you can prove this integral using the Ramanujan's master theorem. Okay, so if you're a mathematician, you have at least one favorite proof of this identity. And if you didn't previously have one, now you do. Okay. Any questions? All right. So we'll conclude there.